Ever wished you could just like float around like an astronaut, to experience that weightlessness of space, but without actually having to, well, rocket off the planet?
Yeah, without the whole spacesuit and rocket thing.
Exactly. Well, today we're diving into the world of microgravity research.
Oh, cool.
It's all about how scientists are simulating those conditions right here on Earth.
It's amazing, really. Researchers get so creative mimicking that low-gravity environment of space, to unlock all kinds of scientific secrets.
Yeah, secrets that would be nearly impossible to discover otherwise. And our guide for this deep dive, well, it's an article by William L. Weaver.
Oh, I know him.
From February 2002, so it's a bit of a time capsule.
Ah, neat.
It's going to show us how they were tackling these challenges back then.
And what's interesting is that so many of those core principles they were using back then, they still hold up today.
Even as technology has advanced so much.
Leaps and bounds.
Okay, so first things first. Microgravity. What does it actually mean? It's not zero gravity, right?
Right, not quite. Think of it more like, well, it is reduced gravity, but drastically reduced. Imagine the gravity you feel here on Earth dialed down to about 1/1,000,000th of its strength.
1/1,000,000th. Okay, my brain is trying to wrap itself around that.
Yeah, it's mind-boggling.
Is there a way to relate that to something, we'd actually experience here?
Okay. How about this? That split second when you're at the top of a roller coaster.
Oh, yeah.
Right. When you feel that weightless sensation just before gravity yanks you back down. That's like a tiny, tiny taste of what microgravity is like.
Okay, I can totally picture that. But why bother recreating it? I mean, why are scientists so into microgravity?
Well, it's like hitting the pause button on gravity itself. Then we can really see the other forces and processes that are usually hidden by Earth's gravity.
Ah, okay. So it's like taking an ingredient out of a recipe.
Yeah.
And then you can really taste the other flavors.
Perfect analogy. And in this case, the flavors are how things behave, physically and biologically. And things just act differently when gravity isn't the big boss anymore.
Fascinating. Like what kinds of things?
Well, in his article, Weaver gives some pretty interesting examples, like growing these super pure crystals.
Crystals.
Yeah, in microgravity. And you can use these crystals to make way more efficient electronics. Well, on Earth, gravity creates these currents, convection currents, in liquids. And that can mess up the crystals as they grow, and introduce impurities. But in microgravity, no currents, super pure crystals.
So gravity is messing up our crystals.
Pretty much.
By removing it, we can make these supercrystals.
Exactly. And then more efficient solar panels, brighter LEDs, faster computers, all thanks to microgravity crystals.
Okay, color me intrigued. This all sounds super high tech, but how do they actually create these microgravity conditions on Earth? Are we talking giant centrifuges and stuff?
Well, those have their place, but one method is surprisingly straightforward. Drop towers.
Drop what now?
Basically, a tall tower, like a giant elevator shaft. Scientists drop experiments from the top. Instant free fall.
They just drop things.
Yeah.
Sounds almost too simple.
But it works. Weaver talks about NASA's Glenn Research Center. They have this drop tower, gives you about 2.2 seconds of microgravity.
2.2 seconds. That doesn't seem like a lot of time to do much.
It's definitely a tight window, but researchers are clever. They design these experiments that fit in small capsules and get all their data in just those few seconds.
It's like a science fair project on steroids.
Exactly. You got to get creative to make it work. And NASA even has a program for students. Imagine designing an experiment that can collect all its data in just 2 seconds.
Talk about pressure. But what about experiments that need more than a couple of seconds?
Well, then things get even more interesting. Weaver also talks about this drop tower at the University of Bremen in Germany. Longer free fall, about 4.7 seconds.
4.7 seconds? Well, it's better than 2. What did they do with that?
Okay, so get this. They had to use this delicate piece of equipment called an excimer laser for an experiment.
Uh-oh.
But way too sensitive to survive a drop.
So what did they do?
They kept the laser at the top of the tower. They just dropped a capsule with the experiment and a camera. And to keep the laser beam on target as it fell, they developed a super fast beam steering system.
It's like hitting a moving target with a laser from over 100 meters away while it's falling. That's incredible.
It's wild, right? But it shows you how far researchers will go to get the right conditions.
And all this was back in 2002. Can you imagine what they can do now?
It's mind-blowing to even think about.
Yeah.
And it's not just drop towers that have evolved. There are other methods, too, like parabolic flights. The vomit comet.
Oh, I've heard stories. Maybe we can save those for the next part of our deep dive.
Yeah, we'll definitely explore those, and even the International Space Station next time.
But for now, I'm still stuck on these drop towers. What about you?
It's amazing, just the creativity and resourcefulness of these scientists.
It makes you realize how much we can achieve, even with limitations, right?
Absolutely. We'll be back with part 2 to explore those other exciting frontiers. Don't miss it. Welcome back. We're right in the middle of our microgravity deep dive.
Still thinking about those drop towers and scientists squeezing their experiments into those tiny capsules.
Oh, absolutely. Talk about working under pressure. But as cool as those drop towers are, they just give you these little bursts of microgravity.
Yeah, we left off wondering about experiments that need, more time.
Right, so for longer durations. Well, there's a method that's been used for decades. Parabolic flight.
A vomit comet.
Ha ha ha, yeah, that's the one.
I've heard stories about researchers battling nausea while trying to do science.
Yeah, the nickname is well earned. Basically, it's a specially modified aircraft. They fly in these parabolic arcs. Yeah, like up and down curves. And during those curves, you get these periods of reduced gravity, about 20 to 25 seconds each.
It sounds like a wild ride. I can't imagine trying to focus on an experiment while feeling all those G-forces.
It's definitely not easy. But even with those challenges, parabolic flights have been super important for research.
In what way?
Well, they've helped us understand how things behave in microgravity. Things like combustion, how fluids move, it's all different without Earth's gravity.
So it's like a roller coaster, but for science.
Yeah. A roller coaster that's pushing the boundaries of what we know about the universe.
I like it. But it's not just about the research, right?
Yeah.
Don't they also use those flights to train astronauts?
Oh, absolutely. It's the perfect way to prep for space missions. Astronauts can get used to feeling weightless practice tasks all in a safe environment.
Makes sense. You wouldn't want to send someone up to the space station without, a test drive first.
Exactly. And speaking of the International Space Station, that brings us to, well, the ultimate microgravity lab.
It's like a permanent science outpost in orbit, right? Dedicated to all things space.
Yeah, you got it. The ISS offers something you can't get anywhere else, a place to do experiments for long stretches, sometimes months or even years.
That is incredible. And what kind of research are we talking about?
Well, remember those super pure crystals we talked about from the drop towers?
Oh, yeah.
Scientists on the ISS are taking that to a whole new level, growing even larger and more perfect crystals.
Supercrystals, but even better.
The potential is huge. Think even better, electronics, medicine, all thanks to those crystals.
I'm trying to wrap my head around that. And it's not just crystals up there, right?
Oh, definitely not. They're also using the ISS to study how microgravity affects the human body.
The human body. In what way?
Well, everything from bone density and muscle mass to heart health, even how our genes work.
So it's like this massive human biology experiment figuring out how we adapt or don't adapt to being in space long term.
Exactly. And that's not just important for space exploration, but also for us back here on Earth.
Oh, how so?
For example, understanding bone loss and microgravity could help us develop treatments for osteoporosis here.
That's amazing. Studying something as out there as microgravity could actually help us here at home.
It just goes to show how interconnected science is. What we learn in one area can have these ripple effects in others you'd never expect.
This is all blowing my mind, but we've been talking about this article from 2002, and I'm curious, has the tech changed much since then? I mean, are we still relying on those same techniques?
That's a great question. And you're right, technology has made huge strides since then. One big area is miniaturization.
Miniaturization.
Making things smaller. Remember those tiny sensors and data loggers for the drop towers?
Yeah.
Well, now we're talking about lab-on-a-chip tech. Super complex experiments, all happening on a chip the size of your fingernail.
Whoa. So instead of needing bulky, expensive equipment, they can do high-level research with these tiny labs.
It's a game changer. Cheaper, smaller, more experiments, all because of this miniaturization.
I can picture an army of tiny scientists at work up on the ISS.
And it gets even better. With AI and machine learning, these mini labs can actually adapt their experiments based on the data they're collecting.
Wait, hold up. It's like the labs are thinking for themselves.
It's pretty close. And this miniaturization trend, it's happening alongside another big shift. Space is becoming more accessible.
Yeah, with companies like Blue Origin and Virgin Galactic Space, tourism is becoming a reality.
And as that happens, it opens up tons of new opportunities for research. We might see, Universities, companies, even everyday people doing experiments in microgravity.
That would be amazing.
Ah.
A whole new wave of discoveries.
It's an exciting prospect, and it's not just access. The tools themselves are always evolving. We're going to keep pushing the limits of what's possible.
It's incredible to think about how far we've come since those early drop tower experiments.
From simple drops to bioprinting in space, the field has exploded.
It makes you wonder, what's next?
The possibilities are endless. But for now, I think it's time to bring our conversation back down to Earth, at least metaphorically.
Right, before we get lost in the vastness of space.
We've covered so much ground, from drop towers to the ISS.
And we've seen how scientists are constantly pushing the boundaries of what's possible in microgravity.
But there's another side to this story, a deeper layer that we need to explore.
What do you mean?
Well, as we venture further into this realm of scientific discovery, we can't ignore the ethical and philosophical questions that come with it.
Ah, I see where you're going with this. We'll be back with the final part of our deep dive to explore those uncharted territories. Welcome back to the deep dive. We've been talking all about microgravity research, simulating weightlessness, those supercrystals, the ISS.
It's a fascinating field, so much potential, so much to discover.
Exactly. But, as we delve deeper into all this cutting-edge science, we start bumping into some bigger questions.
Oh, absolutely. It's not just about the science itself. It's about the impact it has on us as humans.
So, like, ethical questions.
Exactly. Ethical and philosophical questions.
Okay, like what kind of dilemmas come up with microgravity research?
Well, one that's been around for a while is ownership. Like, who owns the discoveries made in space?
Ah, I see.
Say a company funds research on the ISS. Do they own the results? Or should it be shared with everyone?
That's a tough one, especially when you think about how valuable some of these discoveries could be.
And it gets even trickier when you think about things like, bioprinting organs in space.
Bioprinting organs.
Yeah, like using 3D printing to create human organs.
Wow.
But then who has the right to those organs? How do we make sure it's ethical? It gets complicated fast.
Definitely some big questions to think about. And I guess it's not just about the legal stuff, right? There's a whole philosophical side to this, too.
Absolutely. For centuries, we've based our understanding of science on our experiences here on Earth with gravity.
Makes sense.
But with microgravity, we're seeing that a lot of those rules, they kind of go out the window.
So what we thought we knew might not be the whole story.
It's like we're peeling back another layer of reality and finding a whole new set of possibilities.
And challenges, too, I bet.
Oh, for sure. It makes you wonder about our place in the universe, If life can exist in these extreme environments, what does that mean for us?
It's both mind-blowing and kind of humbling, isn't it?
Totally. And it's that sense of wonder, that drive to explore the unknown that keeps pushing science forward.
So as we wrap up our deep dive into microgravity research, I'm left with this mix of excitement and a sense of, responsibility.
I agree. There's so much potential for good, but we need to approach it carefully and ethically.
We've come a long way from those early drop tower experiments William Weaver's writing about back in 2002.
Yeah, it's amazing how quickly things are evolving.
And as technology keeps advancing, who knows what the future holds for microgravity research?
The possibilities are endless.
So to our listeners, we leave you with this thought. What mysteries of space would you want to see unravel? What questions would you ask if you had the chance to do an experiment in microgravity?
Let your imagination run wild. Maybe you'll be the next pioneer pushing the boundaries of science in the incredible world of microgravity.
Thanks for joining us on the Deep Dive.